Okay, cool. So for number 2, so it's a Pokemon question. It's really, yeah, I know people do have strong feeling about this question. Okay, let's look at part A. What's the expected number of Pokemon you have to catch before you catch a Magikarp? So this is actually a relatively standard geometric distribution, right? So if I define X as the expected number of Pokemons you have to catch before you catch a Magikarp, each time when you catch a Pokemon, you have the probability B of catching of it being a Magikarp. So X is follows the distribution, the geometric distribution with parameter P. So the expectation of X will be 1 over P. Yes. And for part B, wow, it's arguably the hardest question in the exam, so we'll go through this one slowly. Suppose you and your friend are out catching Pokemon. Each of you catches 1 Pokemon per minute. Both of you continue to catch Pokemon until both of you have found Magikarp. So what this actually means that both people stops whenever the later whoever is the later one stops. So if you actually catches a Magikarp first, but your friend hasn't catches the Magikarp yet, you still need to keep catching Pokemon until your friends also catch a Magikarp, and at that point both of you stop. Okay, so this is what the question actually is asking for. So what's the expected number that takes you for you to stop? Okay, let's define y being the time until you catch Magikarp, and f being the time until your friend catch Magikarp. Okay, so if we define x as the expected number, expected time it takes you to stop, it actually is the maximum of y and f. Okay, so now we're asking for the expectation of x. This it's easier to calculate this by telsum. So telsum gives this equation. Expectation of x is equal to I equal to 0 up until infinity. Probability of x is greater than I. So if we use this equation, we can get E of x. So now we need to worry about what's probability that x is greater than I. So let me erase what I've been. Okay. So wait a second. Okay, cool. Now we have probability of x is greater than I. So given that x is the max of y and f, probability that x is greater than I is equal to the probability that either y is greater than I or f is greater than I. So if either one is greater than I, the max of them is greater than I. So this is actually equivalent, and then this can be further break down by probability of y greater than I plus probability of f greater than I minus the probability that y is greater than I intersect f is greater than I. Right? Because if I draw a picture like this, if this is the first event, y is greater than I, there's a second event, f is greater than I, then the union is this area, right? So I calculated by probability of this plus the probability of this, and then minus their intersection because it's double counted. So what's the probability? Okay, I'll put it here. What's the probability that y is greater than I? The probability of this is saying like, okay, you haven't catch a Magikarp at time y. So basically means at the first I times that you catch Pokemon, they're all not Magikarp. So I will have 1 minus p, which is probability that you didn't catch Magikarp, to the power of I. So this is the probability that y is greater than I. Similar for f. So f is actually the same. because you both have the probability P of catching a Magikarp each time. So 1 minus P for not catching a Magikarp. So their intersection, since Y and F are actually independent, so what you catch is independent of what your friend is catching. So the probability of their intersection is just the probability of Y greater than I times the probability of F is greater than I. So it's equal to 1 minus P to the power of I to the power of 2. Okay? So now we get this. If we further simplify this, we get 2 times 1 minus P to the power of I minus 1 minus P to the power of 2I. Now that we know, okay, this is really noisy. Now that we know what probability of X is greater than I, we can calculate the tail sum here. So this is equal to, realize we are given a summation equation to use here, so we can apply this. So actually this, instead of being K, should be I. Okay, C to the power of I is equal to 1 over 1 minus C. So the C in this case is 2 times 1 minus P. So we have 1 over 1 minus 2 times 1 minus P to the power. Okay, this is the first part. For this part, the C is 1 minus P to the power of 2. So minus 1 over 1 minus 1 minus P to the power of 2. So eventually this is our answer for this question. And you can either choose to further simplify it or leave it in this form. Okay, cool. This is the second part. Any questions on this part? Yes, please.
So, can you only use tail sum for this question?
Well, you don't really. This is not the only option, but it's the easier one, since actually I provide a equation here to choose, like, to use, right? You can also use something like, okay, what's the probability that X, well, I think the solution actually, the official solution actually provides some other alternative solution, but I'm not too sure if it's alternative in how to calculate probability of X is greater than I, or how to calculate the expectation.
It's alternative how to calculate PRX is greater than I.
Oh, okay, so I guess tail sum is the easiest way to calculate this. Yeah. Yes, please.
Why is the 2 with the 1 minus P on the bottom? Because I thought it was only 1 minus P to the I, and 2 is like a constant. Could you?
Okay, so the question is, why is it a constant factor of 2, right? No.
When you calculate the tail sum.
Oh, okay, so yeah, so why it has the 2 here?
Yeah, why is it attached there? Because it's not raised to the I.
Oh, yeah, you're right. Sorry, it's my bad. I think the 2 should be here. It actually should be here, right? 2 times it. Yeah, you're right. Great. Any more questions? Okay, no. Let's go to question 3. Suppose that you catch part C. Suppose that you catch a Pokemon with probability Q every minute. What's the distribution of the time before you catch your first Pokemon? So this is a geometric distribution with parameter Q. So this is because for every minute, so our unit of time, it's still discrete, it's per minute, so we use geometric instead of exponential. There are answers that uses exponential, and I think these kind of answers are reward partial credits, but actually here it's a geometric. Okay. So part D, very similar. Suppose again that you catch a Pokemon with probability Q every minute. What's the distribution of the time before you catch your first Magikarp? So before we have parameter Q here, because that's the probability that we catch a Pokemon. However, here the event we care about is we catch Magikarp. So first we have probability Q of catching a Pokemon, and we have probability P of the Pokemon being a Magikarp. So P times Q, Q times P is the probability that we catch a Magikarp. So this is also a geometric distribution. but the parameter is p times q instead. Okay. For part E, suppose that people catch Pokemon until they catch a Magikarp, at which point they stop. What's the expected number of Pokemon you and your 100,000 friend have to catch before you all catch Magikarp? So this is slightly different from part B because it says at which point they stop, meaning that for each person they stop right after themselves catching a Magikarp, so they don't wait for other people to catch a Magikarp. So they stop whenever they finish. So this becomes a linearity of expectation. If I use xi to denote the number of Pokemon that ith person catch before they catch a Magikarp, then expectation of xi is just a geometric distribution, right? 1 over probability of p. Okay, so for all person, for everybody, xi, x1 plus up until x 100,001 is equal to 100,001 over p. So this is the expected number of Pokemons you and your friend catch before every one of you get before each one catch a Magikarp. Okay, so part F. Suppose again that people catch Pokemon until they catch a Magikarp, at which point they stop. What's the probability that the total number of Pokemon caught by you and your 100,000 friend is greater than x? Compute the best bound you can. Assume the central limit theorem applies. Here it's actually not very accurate to see it's a bound. It's actually approximation. Because central limit theorem just state that the distribution of Sn approximate the normal distribution. It's not really a bound. So we actually award, since it's not clearly worded, so there are partial credits for using bounds to solve this problem. But now I will do the central limit theorem one. Okay, so we define Sn as the summation of x1 up until x 100,001. Okay, so x is the same definition as it was in part E. Okay, so expectation of Sn is equal to 100,001 over p. Okay, so according to central limit theorem, Sn approximate is approaches the normal distribution with mu being 100,001 p and the variance. Okay, sorry, I forgot to write down the variance of Sn. Okay, equals n times 1 minus p over p squared. Okay, so n is 100,001. Sorry, I don't want to write it down because this is so long, so I would just use n to replace it. So n times 1 minus p over p squared. Actually, here I'll also use n instead. Okay, so now we need to shift and scale Sn so that it will tend to standard normal distribution. So we define Sn prime to be equal to the Sn minus its expectation, n over p, divided by its standard deviation. So it's square root of variance, which is square root of n times 1 minus p over p squared. So this new distribution, this new random variable approaches n with expectation 0 and variance 1. Okay, cool. So then you can calculate the probability of Sn is greater than x is equal to the probability of Sn prime is greater than x minus n over p over n times 1 minus p over p squared. Okay, so you can calculate this probability further, either by integrating the integrating the PDF of normal distribution, dt, from x minus n over p over square root of n 1 over p squared to infinity, or you can choose to do CDF, 1 minus CDF of x minus n over p over square root of n times 1 minus p over p squared. Okay, so both ways are okay from this point. Okay, great.